Hello everyone, welcome to EnviroPioneers. In this video, we will learn the concept of atmospheric pressure. Atmospheric pressure is one of the basic weather elements and a significant factor in weather forecasting because variations in the atmospheric pressure generate winds that in turn can bring the changes in the temperature and humidity. Thus, in this video, we will explore what atmospheric pressure is, how it varies, and how it is measured using different instruments. As we learned in the first video of this playlist, that atmosphere is the layer of air surrounding the earth and air is mixture of gases. So in the atmosphere, these atoms and molecules they move continuously in all direction means they have the constant random motion and during their movement they may collide with the surfaces. So each molecule in the atmosphere is too small and these exert a very small amount of force. But if we sum the total forces from the large number of molecules that strike a surface each moment, then the total observed pressure can be considerable. So here comes the concept of atmospheric pressure. The term pressure is defined as the amount of force applied per unit area. So, the atmospheric pressure, which is also known as the air pressure, is the force exerted per unit area by the weight of air column above a specific location on the earth. So, the atmospheric pressure at any point represents the weight of air molecules in an imaginary column having unit cross sectional area which extends from that particular point to the upper limit of the atmosphere. As we can see, this column extends from sea level to the top of atmosphere. If there is column of air 1 square inch in cross section measured from sea level to the top of atmosphere, the air would weigh about 14.7 pounds. Thus, the average atmospheric pressure at sea level is about 14.7 pounds per square inch. This value is equivalent to 1 kg per square centimeter or 10 to power 4 kg per square meter. Means if we are considering a column of air having the cross sectional area of 1 meter square which extends from the sea level to the top of atmosphere. In terms of kilo, the air mass would be 10 to power 4 kg. As pressure is force per unit area, in case of atmospheric pressure, the force is the weight of air column which is calculated above unit cross sectional area. Now this area can be in terms of a square inch, square centimeter or square meter. So we can say that the atmospheric pressure is the weight of air above a particular location. Here we have three definitions just for the reference. Mass refers to the amount of matter, density is the mass per unit volume, and pressure is the force per unit area. And in the case of atmospheric pressure, we can say it is weight per unit area. Due to Earth's gravity, the molecules are concentrated in the lower atmosphere. As we can see, these molecules are very tightly packed and are close to each other. But in the upper atmosphere, the number of molecules are less and they are scattered in the atmosphere, means they are far away from each other. As density is the amount of mass in a given volume, if we consider this much volume at three different altitudes, the density will be maximum near to the Earth's surface because here we have more number of molecules in this volume of air. But as we move up in the atmosphere within the same volume, now the number of molecule is less and it further decreases as we move higher in the altitude. Thus, density of air is maximum near to the Earth's surface and decreases with increase in height. The upper layer of the Earth's atmosphere may extend up to 10,000 km, but 50% of the air molecules in the atmosphere are present within 5.6 km from the surface. And as elevation increases, the number of molecule decreases and the density of air also decreases. Thus, depending upon the altitude at which the atmospheric pressure is measured, the value may vary. For example, suppose if we are standing on the Earth's surface. So, for this particular point, the molecule in the entire column, means from the Earth's surface to the top of atmosphere, will contribute to the atmospheric pressure. But suppose if we are at this altitude, now the air molecules which are present above this height, means from this altitude to the top of atmosphere, will contribute to the atmospheric pressure. Thus we can say that the pressure at any given altitude in the atmosphere is equal to the weight of air directly above that point. As we ascend through the atmosphere, there is less air above us, and as a result, the air becomes less dense, and therefore, there is corresponding decrease in pressure with an increase in altitude. This image is representation of change in pressure with altitude. So here on the x-axis we have the pressure in millibar, and on the y-axis we have the altitude in kilometer and altitude in mile. And these values represent the concentration of the atmosphere. As we can see, 50% of the air mass is within 5.5 kilometer. 90% of air mass is within nearly 16 to 17 kilometer. 99% of the air mass is within 31 to 32 kilometer. This red line represents the value of atmospheric pressure at different altitude. So we can see that the rate at which pressure decreases with altitude is not constant. The rate of decrease is much greater near the Earth's surface where pressure is high. As we can see, for this much altitude, the pressure decreases from 1000 millibar to 100 millibar. But upper in the atmosphere where pressure is low, the rate of change is not much. As we can see, from the altitude of 20 kilometer to approximately 50 kilometer, the change in the value of atmospheric pressure is from 50 millibar to 1 millibar. As density decreases with altitude, the term thin air is normally associated with the mountainous regions. In meteorology, thin air refers to the lower density and reduced pressure of the atmosphere at higher altitudes. Because of thin air at higher altitudes, most of the climbers who reach the summit of Mount Everest use supplementary oxygen for the final portion of their journey. Even with the help of supplementary oxygen, most of these climbers experience periods of disorientation because of an inadequate supply of oxygen to their brains. And this decrease in pressure with altitude also affects the boiling temperature of water. As atmospheric pressure varies with height, it is difficult to compare the air pressure at ground level from one location to another, especially when the elevations of each site differ. Thus, atmospheric pressure is reported at sea level to make the measurements consistent, comparable, and meaningful. This atmospheric pressure is usually expressed in pounds per square inch but can also be expressed in millimeters of mercury, millibars, dynes per square centimeter, standard atmosphere, or kilopascal. Atmospheric pressure at sea level is referred as standard sea level pressure, and it represents the average pressure of the Earth's atmosphere at sea level under standard condition, which is defined as a temperature of 15 degrees Celsius. So these are the values of the standard sea level pressure which are represented in different units. So standard sea level pressure is equal to 760 mm of mercury or 29.92 inches of mercury. It is also equal to 14.7 pounds per square inch, 1013.25 into 10 to power 3 dynes per square centimeter, 1013.25 millibars 1 atmosphere, or we can say 101.325 kilopascal. So we have to remember these two: 760 of mercury or 29.92 inches of mercury, 14.7 pounds per square inch. And these three are interrelated. So we can see the relationship between them. Under conditions typically found at sea level, the atmosphere exerts a pressure of 101325 pascal. 1 millibar is equal to 100 pascal. So the same value can be written as 1013.25 millibar. Similarly, 1 hectopascal is equal to 100 pascal. This term hecto means 100, and this 100 pascal means 1 millibar. So the value of standard sea level pressure in terms of millibar and hectopascal will be same. That will be 1013.25 millibar or 1013.25 hectopascal. Now 1 kilopascal means 1000 pascal. So the same value is written here as 101.325 kilopascal. Now this term millibar, it comes from the original term for pressure, bar. Bar is from the Greek word baros, meaning weight, and 1 millibar is 1,000th of a bar and is approximately equal to 1,000 dynes. Now this 1 dyne is the amount of force it takes to accelerate an object with a mass of 1 gram at the rate of 1 centimeter square. So 1 millibar is equal to 1000 dyne. So 1013.25 millibar can be written as 1013.25 into 10 to power 3 dynes per square centimeter. Now this 10 to power 3 comes from here. Till now, in this video, we learnt about the vertical variation of atmospheric pressure. We saw that atmospheric pressure decreases with altitude because the density of the atmosphere decreases. Now we will learn about the horizontal variations in the air pressure or atmospheric pressure. Though the pressure changes with altitude are important, but the meteorologists are more interested in the pressure differences that occur horizontally across the globe, and to compare the pressure readings from various weather stations. Compensation are made for the elevation of each station. Means all the pressure measurements are converted to sea level equivalents. A comparison of pressure records from around the globe reveals that the horizontal variation in air pressure is less in comparison to vertical pressure. In horizontal variation, extreme pressure readings are rarely greater than 30 millibars or 1 inch of mercury above average sea level pressure, or 60 millibars, that is about 2 inches below average sea level pressure. Horizontal variation in air pressure over the Earth's surface are determined from barometric readings which are taken at hundreds of weather stations, and these readings are corrected for the sea level, and these corrected data are shown on surface weather maps by means of isobars. Now this term isobar is made up of two words, iso and bar. Iso means equal and bar means pressure. So if we connect all the location or places having equal pressure through a line, that line will be referred as an isobar. So the isobars are the imaginary lines drawn on a weather map that connect the points having equal atmospheric pressure at a given time. As the horizontal variation of atmospheric pressure is less, these isobars are usually drawn at fixed intervals like 4 millibar or 4 hectopascal, and these lines never intersect or cross. These are common intervals which are used in the map preparation. Interval of 4 hectopascal or 4 millibar is used for the synoptic scale weather maps. Interval of 2 hectopascal or 2 millibar is used for the high resolution map, and interval of 1 hectopascal or 1 millibar is used for the local or mesoscale analysis. The spacing of the isobars, that is the distance between these lines, indicate the amount of pressure change occurring over a given distance and is expressed as the pressure gradient. If the isobars are closely spaced, it indicates a steep pressure gradient, means the rate of pressure change for a small distance is much high, and it also indicates strong winds. But if the isobars are widely spaced, it indicates a weak pressure gradient, means the rate of pressure change with distance is less, and these type of isobars represent light winds. Within the map of atmospheric pressure, low pressure areas are marked as L, and here pressure decreases towards the center. As we can see, the values 1004, 1996. At these places, wind converges inward and weather is mainly cloudy, rainy, or stormy. The area of high pressure are marked as H, and here pressure increases towards the center. As we can see here, 1020, 1024, 1028. And in these area, winds diverge outward and there is clear sky and stable condition in these areas. Horizontal variation in atmospheric pressure is mainly because of the influence of temperature and water vapor as well as the flow of air mass. So now we will learn about these two factors which are responsible for horizontal variation in the atmospheric pressure. So first we have the influence of temperature and water vapor on the air pressure. So, this temperature is a measure of average molecular motion, that is, kinetic energy of a substance. At low temperature, cold air is composed of comparatively slow moving gas molecules, and these are packed closely together. Thus, the density of the cold air is more. But when the temperature is high, in warm air, these molecules move faster and they spread further apart, and because of this expansion, the density of the warm air decreases. Now, if we compare two columns of air mass in which one is cold and another is warm, in air column having low temperature, there will be slow molecular motion and the molecules will be compactly packed. Thus, the density of this column of air will increase, and because of increase in density, total mass increases and thus the pressure it exerts on the surface also increases. Thus, the cold air mass has high barometric pressure. While in the column having high temperature, molecules move faster, and because of expansion of these molecules, the density decreases. And because of this reason, warm air mass have low barometric pressure. Thus, we can say that temperature has an inverse effect on the air pressure. As temperature increases, air pressure decreases, and as the temperature decreases, air pressure increases. And this is mainly because warmer air expands and become less dense, which causes the air pressure to drop. While in the cooler air, because of contraction, air density increases. This leads to higher pressure. Apart from temperature, the amount of water vapor contained in a volume of air also influences its density, because as the water content of an air mass increases, lighter water vapor molecules displace heavier nitrogen and oxygen molecules. As we can see the comparison of a dry air and humid air. In the dry air, we have the oxygen, nitrogen, and carbon dioxide as the component. But when water vapor is added into the atmosphere, that is in the case of humid air, the water vapor molecules can replace either of these components. As shown in this representation, three oxygen molecules are replaced by three water molecules. And we can see the molecular weight of water is 18, and it is much lighter in comparison to oxygen, whose molecular weight is 32, carbon dioxide, whose molecular weight is 44, and nitrogen, whose molecular weight is 28. So, thus it is mentioned here that lighter water vapor molecules displace heavier nitrogen and oxygen molecules, and humid air is lighter in comparison to dry air. Thus, it is less dense in comparison to the dry air. So, both temperature and humidity influence the atmospheric pressure by affecting the density of the atmosphere. On the basis of this concept, we can say a cold, dry air mass will produce higher surface pressure in comparison to warm, humid air mass, because both these factors will decrease the air density and thus the barometric pressure will decrease. Now, if we compare warm, dry air mass with warm, humid air mass, this one will exhibit higher pressure, because in humid air the density will decrease, which will result in the decrease of atmospheric pressure. Thus, large air masses are responsible for some of the pressure variations observed at the Earth's surface. Atmospheric pressure at any particular location is also affected by the movement of air. For example, at the locations where there is net flow of air into a region, means there is inflow of air from different direction. So the air piles up here and it rises vertically in the atmosphere. So it results a heavier air column in this particular location and it exerts more pressure at the surface. In contrast, in those areas where there is net outflow of air, and because of this, the surface pressure in this particular area will drop. The pressure variation because of the airflow is little complicated phenomena, because the divergence at the surface, it is accompanied by the convergence higher in the atmosphere. So when we have such type of condition, the surface pressure will rise when convergence is more than divergence, and surface pressure will fall when divergence is more than convergence. We are not going much in detail in this particular topic at this stage, but for now, we should know that airflow, temperature, and humidity, these are the factors that influence the horizontal variation of the atmospheric pressure. Now, coming to the measurement of atmospheric pressure, which is done using the barometer. And as this air pressure or atmospheric pressure is measured with a barometer, it is also commonly called as barometric pressure. There are three types of barometer that can be used for measuring the atmospheric pressure. These are mercury barometer, aneroid barometer, and digital barometer. So let us learn about these one by one. So we will start with the mercury barometer. So this is the oldest type of barometer which was invented by Torricelli, who was the student of famous Italian scientist Galileo, and this was invented in 1643. Torricelli described the atmosphere as a vast ocean of air that exerts pressure on the Earth's surface. And to measure this force, he closed one end of a glass tube and filled it with mercury, and then inverted the tube into a dish of mercury. He found that the mercury flowed out of the tube until the weight of the mercury column was balanced by the pressure exerted on the surface of the mercury by the air above. In other words, we can say the weight of the mercury in the column equaled the weight of similar diameter column of air that extended from the ground to the top of the atmosphere. Torricelli also noted that when air pressure increases, the mercury in the tube rises, and opposite happened that when air pressure decreases, the height of the column of mercury also decreases. Thus, the height of the column of mercury became the measure of the air pressure in inches of mercury. And with some refinements, the mercury barometer invented by Torricelli is still the standard pressure measuring instrument. And the standard atmospheric pressure at sea level equals 29.92 inches or 760 millimeters of mercury. In the barometer, any liquid can be used, but mercury is preferred because it has a high density, low vapor pressure, and it does not stick to glass, which allows for short, manageable column height, and it provides the accurate reading. This high density is the most favorable condition because it indicates that atmospheric pressure can be balanced by a relatively short column of mercury, making the instrument compact. Suppose if we use the water instead of mercury, then because this water is less dense, it would need a tube of length of approximately 10 meter to represent the same amount of pressure. Thus, a mercury barometer is much more practical. Next is aneroid barometer. The need for a smaller and more portable instrument for measuring the atmospheric pressure led to the development of aneroid barometer. The term aneroid means without liquid. So, in this barometer, instead of having a mercury column, partially evacuated metal chamber is used, and this chamber is very sensitive to variations in air pressure and it changes shape accordingly. When atmospheric pressure increases, this chamber get compressed, and as atmospheric pressure decreases, it expands. So this inward and outward movement of this chamber is transmitted through a series of lever to a pointer on a dial, and this is calibrated to read in inches of mercury or in millibars, and the accuracy of the reading depends upon the size of the metal chamber. If the chamber is large, accuracy will be better. Aneroid barometers are also designed for home use, and these include the words fair, change, rain, stormy, or very dry. So the fair weather it corresponds with the high pressure reading, whereas the rain is associated with the low pressure. Though these barometers, which are designed for home use, may indicate the present weather, but to predict the weather in a local area, the change in air pressure over the past few hours is more important than the current pressure reading. When aneroid barometer is connected to a recording mechanism, the resulting instrument is a barograph, which provides a continuous record of the pressure changes with the passage of time. Aneroid barometer can also be designed to be used as an altitude barometer or pressure altimeter, which is an instrument that measures the altitude by using a barometer to detect the changes in atmospheric pressure. Next, we have digital barometers, which are also referred as the electronic pressure sensors. So, a digital barometer is an electronic instrument that measures the atmospheric pressure using advanced sensors and displays the readings in a digital format. So, these digital barometer use electronic pressure sensor, commonly MEMS, piezoresistive or capacitive sensors to detect the changes in atmospheric pressure, and the signal is processed by an internal microprocessor and it is displayed as hectopascal, millibar, or pascal or in mmHg. And many digital barometers also provide altitude, temperature, and humidity readings. MEMS sensors, that is micro electromechanical systems, these are tiny silicon based sensors containing a flexible diaphragm and a capacitive plate. So when atmospheric pressure changes, the diaphragm bend, which changes the capacitance, and it is converted into digital pressure data. Piezoresistive sensors contain the materials that change electrical resistance when pressure is applied. So, when pressure increases, material compresses and resistance changes. And this change in resistance is converted to electrical signal, which through the help of microprocessor is converted to digital reading. And the capacitive sensors use changes in capacitance between two plates as the pressure deforms one of them. So, this was all under the topic atmospheric pressure. We learned about the vertical and horizontal variation and the instrument used to measure the atmospheric pressure. Do you know when airplanes take off or land, some people experience pain in the ear. So, this condition is referred as the airplane ear, and this is the stress on the eardrum that happens when the air pressure in the middle ear and the air pressure outside the ear are out of balance. So, normally the air pressure in the middle ear is the same as the pressure of the surrounding atmosphere, and this pressure is balanced through a narrow passage called the eustachian tube that connects the middle ear to the back of the nose and throat. So, this eustachian tube keeps the air pressure even. But if this eustachian tube is blocked, either because of cold or medical condition, it prevents the flow of air either into or out of the middle ear. So, when the plane ascends or descends, the resulting pressure change can cause discomfort or sharp pain in the ear, and it generally subsides when the ear pop to equalize the pressure. So these are the references from where the content of this video is taken. You can refer to the book The Atmosphere and Introduction to Meteorology. The rest four are the websites where you can get the information about the atmospheric pressure. We will meet soon in the next video. Thank you and best wishes.